So we have remove invalid parentheses problem here. So essentially we're given a string and there are a certain amount of left and right or open or close parentheses. So your goal is to match them so they're a valid pair of valid number pairs of parentheses, and you can ignore all the non-parentheses char, and let's jump right into it. So essentially the approach would be first you figure out what is the number of redundant open and the number of redundant close parentheses. You keep that in counter, and then since the problem asks for all possible results, it's always good to resort to DFS when you're asked for all possibilities. And then, given this open and close counter, we will remove randomly any combination number of open and close parentheses. But how do we know that it is valid? We will simply just run again this helper function if it has zero number of redundant open parentheses and zero number of close parentheses, then it is valid. And what do I mean by redundant number of close and open parentheses? For example, here in this example, you can see that we have one redundant close parentheses. So if we remove this guy right here or this guy right here, they would be a valid pair. So for redundant open parentheses, we can see in the example here, these four guys, they form a valid string. And however, this substring right here, you can see that there's one redundant open parentheses. And then for this example right here, there's one redundant open parentheses. So you can remove one of the three guys right here, and you can remove one of the two guys right here to form a valid string. So let's jump right into it. So first we want a helper function to help us get the number of open and close parentheses. We'll call it count open, we'll call it count redundant, and input will be s, of course, and we'll handle that later. Count redundant string. And once we have that, we'll just have a result empty list, and since we mentioned before, we asked for all possible results. It's always good to use DFS for such statement. So then we will have a DFS, and what we'll input here will of course have original string and open and close counter. We'll also have the start just to mark what's the starting point of current recursion, and lastly we'll have the results for recording all the value, and then we return the results. And this is our depth first search. So we have the string, we have the open and close counter, have the starting point, and we have the results. And of course, the starting point, we will start with index 0. And for our access statement for DFS, what do you think the access statement should be? So since our goal is to remove a randomized openness, close parentheses, of course, given the number. We only stop when there's no more both open and close parentheses to be removed. So for example, if we have one redundant open parentheses and one redundant close parentheses, we stop once we remove one open parentheses and one close parentheses. So the exit statement should be if open equal to 0 and close equal to 0. That's when we stop. Then we will record the string. And like we mentioned before, the third step is to see if this randomized removed version is valid. So we will define a valid helper function and we throw the current string in. And if it's valid, we will append that to the result. And here we directly append the results since we will directly modify on this input string as we go down the recursion. And then we will do a scan of the string. So for index in range of starting from start and end at the length of the list. So if index bigger than start and as start index is equal to as the index minus 1, we continue. It looks kind of weird that while we're doing this step here is because, for example, at this step, for example, if we're given a string like this, by removing this open parentheses and this open parentheses, we're essentially achieving the same goal. So this will be open, open, close, close, and this will also be open, open, close, close. They're the same. And we'll go back to this to see why this is necessary for improving performance. Then we'll name the current character as char, and that'll be starting from that'll be at position index. And here's the removal step. So if we still have stuff to remove and it is open, so if open, just for clarity's sake, we will mark it as open bigger than 0. And the current char, it is a open, we can remove it. And how do we remove it is that we simply just skip that index on original string. So self.dfs s until I and starting from position I plus 1. So we skip the current index, so we skip the char, and open minus 1 since we just removed 8 open parentheses. And close remains the same since we didn't do anything regarding close parentheses, and start will remain the same. Or start will actually be indexed since we already just moved to index, and results will remain the same. And if we still have close, so if we still have redundant close parentheses to be removed, and the current char is in fact close parentheses, we can remove it. The same format for remove here. And since we remove a close parentheses, open remain unchanged, and close is reduced by 1, and index and results. And if we have any non-parentheses character, you can see it's just never handled and just leave it as it is. in the original string. And if the current parentheses is open, but there's no more redundant to be removed, we just don't remove it. And same goes for the close parentheses. And now let's work on our helper functions. And like we mentioned before, a string is valid if it has zero number of redundant open parentheses and zero number of close parentheses. So what we can do is simply call the count redundant function we're about to implement and open and close, same format as in the main function. And if open equal to 0 and close equal to 0, it'll return true. So it is a valid string. So once it returns true here, we'll append this valid string to the final return results. And let's jump right back to this two lines right here. So like we mentioned before, if the current index shares the same character as its previous positions, we can simply continue because by removing either one of them, we will get the same result and there's just no point. So by doing this skip, it saves us some time. And then let's go to the last helper function. It was count redundant. And we'll start out by initialize our open and close. They're both 0. So they're the number of redundant parentheses. So then for char in S, and if char equal to open parentheses, so then open plus equal to 1, and if char equal to close parentheses, then if there's open to match it, so if we have open and close, it will form a pair, so it is valid. So if there's open, then open minus equal to 1, so it will reduce by 1. So if there's no open parentheses available, so for example right here, it started out by having a closed parentheses, we know right away that it is a redundant close parentheses. So close plus equal to 1. So we return open and close. So let me restate that open is the number of open parentheses that is unmatched by a closed parentheses, aka is a redundant one. And the closed parentheses is the number of closed parentheses that's never matched or can never find a preceding open parentheses before it, so it is redundant. So let's go through the logic one more time to see if we make any mistake here. So first, we count the number of open and closed redundant parentheses. Then we in a randomized order, remove the required amount of open and close. And we check, and once we remove the required amount, we check if it's valid. If it is valid, then we add that to the final return list. So open close equals to the return value, helper function right here, and we call on DFS, and the exit statement is when we already remove all the redundants. So open equal to 0 and close equal to 0. And if it's indeed a valid string, we add that to the result. And then we go through the string, and this is like we mentioned before for uh, time purposes. We never remove two of the same kind just to save time and get the current char. And if we still have open parentheses to be removed and the current char is an open parentheses, we'll remove it. And the way we remove it is simply by skipping the current index. And since we remove a open parentheses, the number of open parentheses remained to be removed decreased by 1, and the close remain unchanged, and the start will start from index, and the results remain unchanged. And the same logic goes for close. And let's check on our helper function. So a string is valid if it has 0 redundant parentheses, either open or close. So we call count redundant, and if both of them is 0, we return true. And like here, you can see it has 0 redundant parentheses. And let's go to our count redundant. So we start off by declaring open and close with 0, and we scan through the string. And if it's a open parentheses, open increase by 1, and if it is close and there is a open to match it, then we will reduce the open by 1 and the close remain untouched. And if it is a close parentheses, but there is at this moment no preceding open parentheses, the close, so the number of redundant close parentheses, increase by 1. I'll return. And it looks correct. We're trying to compile. So, okay. So add, so it is index, not I. And let's check to see if the other is correct. Okay, it looks correct. Return the correct result, and let's try to submit it. So it works. And let's go for the time and space complexity analysis. So for space complexity, we never introduce any significant extra additional data structure. So it would just be this result right here, which is for return value. We can call it O of n. And for time complexity, even though the code looks super complex, here we do a single scan through, which is all of n, and is run here. So this will be all of n. And for the DFS right here, it will have basically it just go through all the possibilities of combination of open and closed parentheses to be removed. So it will also have a big O of n, since for each, let me see. So this will actually be O of n, and the entire thing will run n times, as there's some n position on the original string. So this will be of a time complexity over n squared. And just to do a recap, so essentially we first found out the number of open and closed redundant parentheses, and we removed that amount of corresponding parentheses, and we check if it's valid. If it's valid, we return it. And that's it.